Hi students, I'm going to do some problems for you in chapter 5, and this is the gas law chapter. And these problems can be found in the packet down here, page 92. And the ones I'm going to do are the ones right here, question 2A and B. But this video is going to be just those two. Before I do that, I'm going to pull this up a little bit so you can see question 1A and B. Those are the answers. So maybe take a pause and note those down. I'm not going to do those problems for you. There's a video on how to do density and the formula to use for density of a gas. It's a really easy to follow video. So follow that video, write down that formula in there, and then you can try those on your own, and those are the answers. You can just double check that you're doing them right. You don't need to see me. It's pretty easy to do. Okay, so I'm going to come down here and do 2A and B. These are gas law stoichiometry problems, and I'm going to talk about them a little bit. I did post a couple videos on gas law stoichiometry already. So these will follow the same general idea as those, but I thought I'd show you, from my perspective, how to do them. And of course, reminder, stoichiometry in general is when we take a balanced chemical reaction and we do calculations with it where we use some of these reaction coefficients in a reaction ratio. And we've done stoichiometry before, a lot of it in chapter 4, you've done it in your lab class. And I always like the fact that we have stoichiometry towards gases towards the end of the semester, because it's a good way to review. Because the thing about gas law stoichiometry is they don't just involve gases. There will be a gas somewhere in there. Over here we got chlorine. But there's other things here. We got solids, you could have them with a solution. So it's pretty much anything that we learned before, we will also take effect now. So let's review that real quick. Let me grab a piece of paper here. Hold on one sec. Okay. Oh, there was some right underneath there. Anyway. Okay. So in general, when we have stoichiometry, that one we always have in the middle, as I always say, is this step. All stoichiometry problems have that, moles of A to moles of B. And the way we get from moles of A to moles of B is what I called back in chapter 4, the reaction ratio, okay, the reaction ratio, the coefficients of the reaction. And in chapter 4 and back in 152, the simplest way was one of these, right? A one-step problem. Given moles of A, how many moles of B do you need or do you produce? But most of the time we don't have moles, we have a starting amount of, a lot of times grams, right? So grams of A, the moles of A is many times our first step. And in order to do that, we need the molar mass. And sometimes at the other end, at the solving end, what they asked us to find is grams of B, and we need the molar mass. So this is a grams to grams problem. You know how to do those. And we also said that, well, sometimes though, the grams works really well if you have something that's pure, that is a solid, it could be solid, liquid, or gas, but it's generally something you can have that's not mixed with a whole bunch of other things. If you have a mixture, then you generally, a lot of times, have a solution. And in a solution, the way we get to moles is with molarity times liters. So molarity of A solution, liters of solution A. And similarly down here, if we have moles of B, we can calculate. The molarity of B, this is molarity, would be the moles of B, which you just calculated in this, over the liters of B. So that's stuff you've been doing in lab, with figuring out the molarity of things. But now that we have gas laws, what we can do here is, it doesn't matter where we start. If we have moles of our unknown, if it asks for grams, we go this way. If it asks for molarity, we have this way. But sometimes with the gas, you're asked to do something with the ideal gas law. Where this is your moles. So for example, they could ask us how many liters of this gas is produced in this reaction, or what pressure would we need to use. Now, the variables here are P, V, N, and T. N is coming from here, so that would be known in the stoichiometry calculation. So that means you'd need to know something about, maybe pressure and temperature in order to calculate volume. Similarly, on the side that where we know things, you could be given P, V, and then have to calculate T. So PV over RT would give you N, which is moles. So instead of giving you the information of the known in terms of, if it's a gas, instead of giving you in terms of grams or molarity, they could tell you you have pressure of, let's say, oxygen, the volume and the temperature, and then it's part of a reaction, so you have to do this. So now we have this really complicated stoichiometry map, but the thing is it all goes through moles. And anything we've done with stoichiometry in the past, besides just the straightforward problem, can happen with one of the unknowns or knowns being a gas as well, like limiting reactant problems or percent yield problems. So anything back from chapter 4 in stoichiometry can happen in a gas law stoichiometry. Okay, so the ones I'm going to do aren't going to be that hard. You'll run into some more difficult ones in the homework and in the packet. Just wanted to point that out. So I'm only going to do a couple examples, and so, but there's almost, think about all the different combinations you could have here. I could start with molarity of a known substance and ask you to find the liters of a gas. I can start with grams and ask you to find the liters of a gas. I can start with pressure here with one gas and then ask you to find the molarity of something over here. So it's really, all over the place. But if you have this and you kind of like draw a map of what you're doing, oh, I'm starting here, I'm going here, I'm going here, it'll help. Okay, so let's look at the problems we're going to work on in this video. So this is problem 2. There's an A and a B on page 92. So here's the reaction. We're going to be using the same reaction for both of them. And we have some good to practice your nomenclature. Potassium permanganate reacting with hydrochloric acid. And we get our products, a lot of products here: water, aqueous potassium chloride, aqueous, this would be manganese 4 chloride. Sometimes they call this manganese dichloride, but don't worry, it's manganese 2 chloride, I should say, not 4. And this is our chlorine gas. So here's the thing where we're going to have a gas in there to do some calculations with. I'm actually going to do part B first. We'll go back and do A, but let's do part B first. And so what it's asking is how many liters of chlorine gas. So it wants to know how many liters of this gas here could be obtained. And then we have the temperature that it's going to be at and the pressure if 10 grams of potassium permanganate is reacted with excess HCl. So in this case, we don't have to worry about the HCl. Of course, it should be pretty obvious. I could easily write this question and give you a molarity in liters of HCl, and it becomes a limiting reactant problem. So if I don't tell you it's excess, you could have to figure that out and show your work. I'm going to go to the next page. I'm going to go to another page and do this because there's not a lot of room here. So I've already copied the reaction down and some of the information on the next page. Yeah. All right, so there's the reaction, and we're looking for liters over here of the chlorine, and this is the temperature and the pressure they gave us. And we're starting with 10 grams. So let's just do a little map here. I'm going to start with my grams of potassium permanganate. I'm going to change that to moles. That's simple with the molar mass step. And then I'm going to go to moles of my chlorine, which is going to be my reaction ratio step. So this is my molar mass, and this is my reaction ratio. And then once I'm at moles of chlorine, I can't just keep going with this map like you normally would with the information I have. Because they want to know liters, they're looking for volume. And so in moles here will be my N. So now I have to go to PV equals nRT. And if I solve PV equals nRT for volume, I get volume equals nRT over P. So the moles here will get fed into there, okay? And I have my temperature, and I have a pressure, and they can go in here. I have to fix the units on the temperature, but when I have all that, I'll be able to get volume. So it's a two-step problem in terms of stoichiometry, and then we feed it into PV equals nRT. So let's just go ahead and work that out. Okay. So I'm going to start with my 10 grams of potassium permanganate over 1, just like in the old days, grams of potassium permanganate in 1 mole. And that's my molar mass, and that is 158.04. I'm going to write it down here to save room. So that's my grams in 1 mole. That would cancel out, and this is moles of potassium permanganate. And now I want to go from moles of potassium permanganate to moles of my gas, chlorine. Sorry, the writing's bad. Chlorine, okay? Still don't like that. Cl2, there we go, to moles of chlorine. So moles here to moles here. That's my reaction ratio. And this is a 5:2 reaction ratio, 5:2. And if you cancel things out in the units, we're at moles of chlorine. If I do that calculation, 10 divided by 158.4 times 5, and then divided by 2, you should get 0.158 moles of chlorine. And you're not done though, that's N, because that's moles. And so now we go to our equation. I'm just going to recopy it, nRT over P. So my N is my 0.58. My R is 0.8206. My temperature has to be in Kelvin because the units on R, I'm not writing it because I don't have a lot of room here, but R has units of liters, atmospheres, moles, and Kelvin. So your temperature on all gas laws has to be in Kelvin. If you change that to Kelvin by adding 273, you should get 313.15 Kelvin. I'll show you that up here. Let's scooch up here a little bit. So we got 40 and 273.15. Can you just use 273? You know, most of the time they come out exactly the same because that 0.15 is very little when you do the whole calculation. I'm so used to 273.15, I use it. So, I mean, if you have a multiple choice question, you know, that could cause a tiny bit of difference, but not so much. So this becomes 313.15, but SigFigs tells us that since the last significant figure was in the ones place up there, we got to round this to the ones place. So 313 would be technically correct. I tend to usually just do a lot of stuff in my calculator and just say, I'm just going to put a line over it to remind me that that's the last SigFig. So it would work if you just did 3.1. Pressure is already in atmospheres. They gave it to us in atmospheres, so 1.2 is good. Remember, that's because the units on R, I'm going to write it up here, 0.08206 liters, atmospheres, moles, Kelvin. So because we're using that, there's other values of R you can look up for different units of pressure and not for temperature, but you can look it up for different units, top units, different volume and pressure units, and you get a slightly different number here. But most of the time we just use this one and convert with that. Okay. So if I do all that, everything cancels out because I've got the right units except for the liters. And my volume comes out to be 3.4 liters. I'm only allowed 2 SigFigs because my pressure only had 2 SigFigs. So that's the answer here. So that tells us that if I was to use this reaction, it's not the safest reaction in the world. You're generating chlorine gas, which is poisonous. But if you react potassium permanganate with hydrochloric acid, you'll get a whole bunch of stuff and you'll generate some chlorine gas. If you run it at 40 degrees Celsius, which is warm, right? Pretty hot because it's, you know, you could calculate that in Fahrenheit and see what it is, but you know, our body temperature is 37. So you get the idea that that's pretty hot. And 1.2 atmospheres is pretty high pressure, right? Normal room pressure is about 1 atmosphere. So you've got to get a higher temperature and pressure. That's how many liters you would have of that gas, 3.4 liters. That would be the volume. Okay, so I'm going to switch over and do the other problem. Let me bring this back here a second. If you need to write that down, I'll just leave it here and you can pause the screen for a second and write it all down. Okay. Hope you're back. Okay, So over here, we're going to go back here. And so we did problem B, and we're going to look at problem A. Now, 2A is almost the same because we're still starting with the 10 grams of potassium permanganate, only now our conditions are different. It's STP, okay, standard temperature and pressure. So we're running the same reaction under the same amount of starting material, but we are going to have the gas that's generated be at a different temperature and pressure. So there's two ways to do this problem when you have STP. I'm going to start with the way that's real simple, similar to what we just did. So the difference in the one we're going to do now is that instead of being this part where you have 40, we're going to have it at STP. Okay, so this is problem A is at STP, and this was for problem B. Now, I hope you realize that this first part doesn't change in problem A. We still start with 10 grams, same molar mass, same reaction ratio, which means if we react 10 grams of potassium permanganate with excess hydrochloric acid, we will still generate 0.158 moles of chlorine gas. The difference is that it's under different conditions, and gases are very sensitive to conditions for their volume because they're very sensitive to temperature and pressure. So we're having different temperature and pressure. So therefore, when we go down to the ideal gas law, we will have different numbers in here. So this part is exactly the same, all right? So this was for problem B. For problem A, when we plug into there, okay, we'll still have volume equals nRT over P, but an N will still be our 0.158 moles we calculated. We'll still have R, but now the temperature is from STP, and standard temperature and pressure is at 0 degrees Celsius, which is in Kelvin 273. So 273.15 Kelvin, and standard pressure is 1 atmosphere, so that's 1, okay? So that's where that comes from. Now, if I do that and do the calculation, the volume you're going to get here is going to be a little bit different, 3.54 liters. Okay. Now, oops, you might say, why did I put, first of all, before we worry about sig figs, let's think about what happened. Over here, we have this under a different conditions, and so we've generated a different amount of liters here, okay? So having it at standard temperature and pressure has affected the liters. Let's think about how it did that. Over here, the temperature was higher here. Now temperature, than here, right? Pretty high compared to this. Temperature has the effect of usually making a gas expand. If you warm it up, it's going to expand. So we have a lower volume here. So it should have expanded, but there's another effect here in that we're also changing the pressure. And so over here, we have a higher pressure, and it's significantly higher than this. From here to here, that's a lot higher than the jump from here to here, okay, if you do it like it's a percentage-wise thing. So although you would expect this one based on temperature alone to have a higher volume for expansion, having that significantly high pressure kept the volume lower, squeezed it in, okay? So that's why this is lower than this number, mostly because of the pressure. Now, why is there 2 sig fig here and 3 here? Well, this we were given this was our pressure. That was our atmosphere. And that had 2 sig figs. When they tell you a pressure of any pressure it's given in the problem like that, you have to assume it's a measured quantity, so it had sig figs with it. Over here, they just said STP. And STP is like an idealized reference state. So we really don't have sig figs attached to it. In other words, this is 1 atmosphere, but you can assume it's exactly 1 atmosphere, okay? 1.000, as many as you need. It's an idealized state, similar with this temperature. You don't have to worry. In other words, STP, if it's just states it, what would it be at STP? It's a reference state. You don't have to worry about the sig figs with it. So the sig figs just came from this moles. That's where it came from, okay? So that's why there's 3 here and 2 here. All right, so that's how you do that. Now, there's another way to do this problem A, because of course, if you had both of these to do and you already had the moles, then this is the easiest way to do it. Just put it on there. But what if you just had problem A first, and you didn't have problem B? There's a shortcut. So if you just have this problem as written, okay, how many liters of chlorine gas could be obtained at STP. You don't have to do it this way, but there is this STP shortcut that I want to mention. Okay, so at STP, 1 mole of gas occupies 22.4 liters. It's called the molar volume. And I posted a video about where that comes from. It's not a mystery. If you didn't see the video, basically all you do is you take this equation here, volume, and you put in 1 for a mole here, and you put in STP, and you get that 22.4. So any gas occupies that same volume at STP. In some people, it's pretty easy number to remember, 224. So if you happen to remember or you have it written down next to you, you can use this for gases that are, but only for at STP. If it's not at STP, you can't use the 22.4. But a lot of problems are given at STP. So how would this help us? Well, we would go back to the original setup we had here, okay, that 10 grams thing that I wrote kind of messy. I'm going to recopy that. So you would say, I've got 10 grams of potassium permanganate, and I have my 158.04 grams in 1 mole of potassium permanganate. And there are 2 moles of potassium permanganate for every 5 moles of chlorine. So far the same that we just did. But now, instead of having to stop, calculate moles, plug it into a formula, if you say, oh wait, I remember this, I can say, let me cancel this off. I can say 1 mole of chlorine occupies 22.4 liters, and I always do this, at STP, to remind me to only use that at STP. So 1 mole of chlorine or anything, at any gas at STP occupies 22.4 liters, and then you just do the problem. And you get your 3.54 liters. So it's a shortcut for STP. And there are some video, I have another video, I think, on there that shows how to do that. But just show there's 2 different ways to do it when you're at STP. Where it gets a little bit bad is that some people remember it wrong, okay? But you know, you're doing this online, so you can always write that down in your note sheet or whatever. But where I do see it become a problem is students, let's say on the final exam, they start throwing that in there for things that aren't gases. They start using it for solids and liquids. You know, some people would say, some people forget, like they don't do this step, and they say, oh, I'll just use that 22.4. You gotta do this step to get to the gas. This has to be for a gas. So it's like any shortcut, you have to use it wisely, okay? But it's there if you need it, helps out in certain problems. And help out in density problems too, but those are pretty easy even without it. So anyway, that's all for this one. I'll make some more videos and some more calculations, but that's enough for this one. Talk to you later.